Good afternoon, everybody. We are back here for the afternoon session, which is about what we can do next for the decarbonization and for the handling of this complicated situation we are in terms of climate change and so on. So first, I'd like to start again with some technical information regarding the protocol. Please, Laura, please put again the slide. The recommendation for the attendees are, please send your question only in the Q&A box, and our speakers will answer them live, as many as possible, during the panel discussion. Again, we will have two more polls, one at just before the break and the other one before the panel discussion. I kindly ask you to do not copy or photograph information displayed during the webinar. All the registered participants will have the material after the meeting. Recommendation for speakers: please keep your cameras on during the webinar. Please mute your microphone when you are not speaking to avoid any background noise. And if you have a speaker's technical issues, please message the administrator via your dedicated chat box. Again, I remember that this webinar is being recorded. Thank you, Laura. And before starting our afternoon session, I prepared one slide during the lunch break, and I would like to show you, because it was said this morning that today is the Earth Day 2021. So we are video conferencing, and I found during the lunch this very recent article published a few days ago, which states that a standard video conferencing service uses about 2.5 gigabytes per hour and has a carbon footprint of 157 grams per carbon dioxide equivalent per hour. So we are here, we have a webinar of 5 hours, so 150 grams per 5 hours per 250 people. It means that, according to this paper, which I assume is correct, we are producing today about 200 kilograms of carbon dioxide for our webinar, so 0.2 tons. Alternatively, until the pandemics, we were used to fly somewhere, and typically for these events to Brussels. And so by flight, there are typically with the planes that are used for short flights, 90 kilograms per hour per passenger. So let's assume 90 kilograms per 2 hours, so 1 hour trip for each of us going to Brussels. It can be more, but let's assume simply 1 hour, so round trip 2 hours. For 250 people, this means 45 tons of carbon dioxide equivalent. So this means that we have emitted 225 times less carbon dioxide than flying to Brussels, doing this online. And here, only flying is considered. Probably some of us would have taken a taxi, would go to a hotel, and so on and so forth. So probably this is a good message to take up for the Earth Day, because maybe we have also to rethink our way of having meetings, at least part of them, for the future. Well, after this short slide, I would like to give the floor to the first speaker, who is from the European Commission, and our speaker is going to be Søren Bøwadt, who is head of unit of the industry unit of the Earth and Digital Executive Agency in Brussels. This body is responsible for the implementation of the industrial research and innovation activities from Horizon 2020, as well as the industry activities in Cluster 4 of Horizon Europe. He has got a PhD from the University of Odense in Denmark and joined the European Commission in 1999. He has a vast experience in international projects, having been responsible for over 150 scientific projects in various areas of natural science. is going to talk about EU initiatives for 2050 carbon neutrality. Thank you very much, Søren. Please, the floor is yours.
Thank you very much, Nicola. I will just try to share my screen. Just a second. Does it work now? Because I can't see anything.
Yes, yes, it works. Go
Okay.
ahead. You can even go to
very good
presentation. Okay.
Okay. Thank you very much for the introduction, and I'm actually honored to be amongst the EuChemS membership today. It's a pleasure to be with colleagues, so I'm really happy about this, especially because I think that I can give you some nice news, which is also related to the to the fact that the Commission has raised its ambition for the carbon targets significantly in the last couple of days, and that was already mentioned this morning, that now they plan to make a law that actually involves 55% reduction of CO2 by 2030. And that is indeed a very tall order. But to the vision in general, I mean, we want to do a sustainable and fair and prosperous future for this planet. And that covers basically every activity that we're doing, including the reuse of carbon, which is the aim of today's webinar. And in terms of budget, the DGRTD and the other services inside the Commission, they have actually pledged to use more than 35% of the budgetary targets from the framework program. And that is a really, really big amount of money that goes into this. I think for the industrial activities, we're probably going to surpass that even quite significantly, so that we are approaching probably 50%. And that should all help to achieve the sustainable development goals, which you can see here in the slide. But at the same time, I think it's important to point out that while we want to conserve the environment, we also need to boost the competitiveness and the growth of the European Union to be able to actually spearhead this direction. And the problem that we have at the moment is one of sustainability. I mean, it's not going to be so easy to do these things. It's very easy on the political side to say, okay, we're going to reduce 35 or 50 or 70% of CO2 in the emissions. But somebody has to do it. And actually, the only way we can do this is by reusing and recycling the resources that we have. And that should happen in a very, very efficient way, because in reality, we can only use the energy once. Energy in that sense is not recyclable. So we can do all these things. We have the technologies in principle for many of them, but they're not honestly efficient enough. And that's actually where you as a community come in, because we need you as chemists to help with all aspects of this process, to make it feasible to use new ways of recycling, but also to make it as efficient as possible. I'm going to give you today just a couple of examples of the initiatives that we do, because honestly speaking, if I would have to go through all the things that are coming in the next couple of years, it would take a couple of hours and it would be really, really boring. So I've taken out two examples, and the first one is the European Green Deal call. You're going to get a second part of that in Robert Mubarak's presentation a little bit later in this afternoon in a different area. This call was already announced when the von der Leyen Commission came on, and it resulted in this call, which has 20 topics and was had a deadline here earlier this year. The indicative budget was nearly 1 billion euro. And as you can see, there was quite a number of proposals submitted, and the total amount requested in these proposals was simply staggering. It's one of the most ambitious, largest of the targeted calls of this kind in the Commission history. Just a little bit of the details, and I'm not going to go through all of these because you can read by yourself, but you can see that it's 10 different areas that covers basically all different kinds of aspects of the green economy. That means both in terms of sustainability, but also in terms of climate, biodiversity, and so on and so forth. And you can see that there's a lot of difference between the different areas in the number of proposals that we've received. And I think that here it's important for me to say that also it's necessary to balance the amount of money and the actual needs. So just because you get a lot of proposals does not mean that there is an equivalent need. In a little bit more detail, you can see the proposals which has been submitted per topic. And you have some which are really, really popular, which is, for instance, the green transition and energy access partnership with Africa. And you have in the middle there, topic 6.1, which is the farm to fork strategy. And then at the end, with 244 proposals, you have enabling citizens to act on climate change. So lots of difference, and also a lot of difference in the way things are structured. But the overall aim is mainly for the Green Deal. Again, just giving you an example here, which is the topic that I was responsible for here earlier this year. And that's the topic which is called 1.3.1, which is closing the industry carbon cycle to combat climate change. And why do I take this example? Well, yes, of course, it's also because I was responsible for that topic. But I think that mainly it's because I think we all realize that the process industry, which this is targeted at, uses 20% of all known resources on the face of this planet. And they also make approximately 20% of the CO2, which is, I think in energy terms, relatively straightforward. But the importance here is that if we can, on this kind of scale, make a real impact, then it's a much easier target than trying to limit the CO2 on a household basis. So that's basically what we are trying to do. And you can see that the budget was 80 million euros, and we received 16 proposals with a requested funding of 500 million euros. So I'm not going to go into all the things about this topic. I think that for me, it's important to say that the aim of this was basically to reduce or to demonstrate that we could reduce over 30% of the current 665 megatons of CO2 emissions, which are related to the energy intensive industries. And at the same time, when we wanted to do this, we also needed to demonstrate the industrial and economic feasibility of doing so that you could produce a product at the end that was valuable for society and had an economic value. And I think everyone who's been dealing with industrial processes know that to reach industrial production level from an idea is not easy. And of course, we are building on the shoulders of others, but we still have a very tall order to be able to do this. And I think that the ambition of this you can actually see in the first line, because we wanted to develop and deploy highly innovative and recyclable catalytic material systems to facilitate this production of chemicals and fuels from industrial flue emissions. And the aim was to have a 50% increase of the overall efficiency compared to the state of the art. This is a very, very tall order. And I think that when we launched this call, many people came back to us and say, this is not going to work. But actually, we did get some proposals. I'm going to go back on that later on. And another crucial aspect of this proposal was that it should demonstrate the full value chain for the industrial production, so that it would include the SMEs also in this, which are much more flexible than the big companies. The practical aspects of the project was that it should have an industrial scale demonstrator operated by 2026, which was based on industrial symbiosis, meaning we should link different actors in the process industry so that we could optimize the use of the CO2 and also create energy efficient catalytic systems that would do the conversion. And at the same time, this demonstrator should be able to show that it would be possible by 2050 to actually reduce this by 2,000 or 200 megatons with a good potential for the carbon intensity also. And also this is not an easy target. And especially when you're considering that this industry we're talking about, the process industry, is heavily dependent on fossil fuels. And all the money that has been put into the infrastructure is not easily disposed of. So it's not something we can just do from one day to the other. Finally, it's supposed to actually increase the level of demonstration with 10 times in comparison to what is presently capable in Europe. Just very briefly, what came out of the evaluation, we had, I said, 16 from the start proposals, but 2 were ineligible. So we had 14 eligible proposals, and we retained 2 proposals and 1 on the reserve list. So in reality, whilst the 2 retained proposals is 56 million euros, in reality, we are actually aiming at 95 million euros in total for the 3 proposals that we hope to be able to fund. The deadline was, as already said, in January earlier this year, and we've had the evaluation, and we expect that the results letters are going to come out here at the end of April or the beginning of May. We are a little bit in limbo at the moment because we are transferring all our activities into the agency, as you could see at the start slide and what also Nicola said. That means that in principle, we should have the first grants signed in August or in September 2021. So that's one action. But then what is actually next? Well, next is also coming here in May, and there we're going to have the launch of Horizon Europe. And I already said that we're going to use more than 35% of the total budget of Horizon Europe towards Green Deal targets. And it's going to focus for our part quite a lot on the so-called safe and sustainable by design. And I'm going to go into that a little bit more in detail later. It's supposed to support the European policy goals and priorities, and it is a systems approach that we want to aim at, so that we have not only sustainability criteria, but also a social empowerment, and that the things that we do have an industrial relevance so that we can all keep our job. And at the same time, there has to be an element of enforcement so that we are sure that we can actually do this and keep the competition at a level. You know, it doesn't matter what we do in here. If we are not able to enforce these things at the end, then we will just have products that are coming from the outside that will not uphold the principles that we are using it. And we aim at a comprehensive concept of sustainability, which is driven by safety and circularity and functionality, so that we really have a comprehensive concept for products through their life cycle. And this is only possible if we can also align the actors across the value chain to also use these sustainability criteria. The policy framework is basically an interplay between several things. You have on one side, you have the Green Deal that are sort of covering the overall aim of what we want to achieve in the framework program. And then you have the chemical strategy for sustainability. It was launched here at the end of last year, and it is one of the most ambitious legislative acts that the Commission has put forward in the last many, many years. I think that us that work in and with the chemical industry in particular, we know exactly how difficult this is going to get to reform the full production of chemistry in such a way that we're not losing the jobs and that we still have the full functionality of the chemistry available to us. Of course, it doesn't go without a few things that needs to be banned. I think there are a couple of things that inevitable will be banned. And I think that earlier you saw this also with the PFAS, which is now targeted for banning in the EU. And it's also an aim to look more into cocktail effects of chemicals when we are assessing risks in general. But at the same time, we want to boost the investments in such a way that we can increase the capacity for safe and sustainable by design chemistry throughout the whole life cycle, because it's a long journey. It's not something that we embark on today and then finish by next year or next year again. This is a 10, 20, 30-year journey that should cover all the aspects of what we do. And of course, an important part of this is to be able to have a resilient supply of chemicals, especially of critical chemicals, so that we can design our way out of criticality instead of suddenly finding out that we need an element which we do not have. And of course, when we're talking about this, we cannot do this without the EU playing a global role, a major global role to lead the way of doing this. Because otherwise it's going to be everyone's fight against everyone. And that's not a good way. I think we've already, with this initiative, shown that we are willing to take the lead in the global terms. And we already know that many of the countries surrounding us, and which we normally compare ourselves to with the States and some in the East, that are looking very much towards what we're doing. I think that the biggest problem that we have at the moment is actually one of making sure that we can meet the expectations. Because on the political level, all these things that we are saying are very easy. On the practical, technical, scientific terms, it's very, very difficult to do. So the approach that we want to do basically goes on to design new materials, new products, ab initio. That means all the way from the raw materials to the use of the needed materials with the functionality we need and the associated processes, so that we're not making a disjoint action. We have mining on one side, and then they do some mining, and then we are trying to make a product for which we do not have the resources. Everything has to be aligned in such a way that new materials are produced efficiently. And at the same time, it should be done in such a way that we involve all the actors in the full value chain. That means, of course, the industry is really important, but your ideas are the start of this process. And we need to have this bilateral work together when we set out for doing this. And we actually already starting to do that, because in the working groups that we have, you have actors coming from academia, you have them from big industry, you have them from regulatory, and so on and so forth. So we're trying to assemble these things, because at the end of the day, as we also know, we can come up with the most fantastic materials if the citizens do not want them, then we have nothing. So therefore, we need to have a social engagement that allows us to do this and makes people understand that chemistry inherently is not necessarily safe. What we need to do is to contain the processes in such a way that they do not become dangerous for them. Okay. So what do we need to do in order to get there? As I said, it's a long journey, and it needs a framework, because we need to develop the criteria that we can use to base this on. What does it mean to be safe? What does it mean to be sustainable? And when you're then putting safe and sustainable together, how do you actually do this? Okay. Which dimensions do you use? How do you measure these kind of things? You need to develop criteria, and they take time. It cannot be that we from day one have some chromed criteria that doesn't work. It needs to be an iterative process. And first we will start to do the frame. Then we will put them more and more accurate until we know for sure how it's being done. And actually the way that we have foreseen to do this is a little bit an iterative way, so that we would start with some easy targets, say for instance some polymers or some metal coatings, or perhaps the surface coatings in general, and then to try and see how can we make those, design those in such a way that they are functional, that they are safe, and that they are also sustainable. And that needs an iterative way. I've been in this business for a long time, not as long as some of the others in the audience, but I mean, I cannot see how you can design this without making an iterative process. And this iterative process needs a community. It needs a community of experts and stakeholders to give input to this process. Otherwise, we're not going to get there. And at the end of the day, what we hope to get out of this is actually that by launching this already now and working very carefully with it, we can reduce the time for research and development and production of new materials quite significantly. And we can, at the same time, we should be able to do this in a very cost-effective, innovative manner. That means we can get new products to the market faster. And we should not forget, this goes hand in hand with regulatory preparedness. And that goes at all ends on the regulatory enforcement at the end, so that we do not have products that do not obey the regulation. And then hopefully at the end of the chain, we will have safer, circular and functional products that have a significant better consumer acceptance, because that's the only way that you can sell the products at the end of the day, and we can keep the jobs in our business. And with that, I would like to thank you for your attention, and then hope that I can answer some of your questions later on. And then back to you, Nicola. Thank you.
Thank you very much, Søren, for this inspiring lecture showing the vision that we need to take up for the challenges that we have ahead of us, which are very, very tough. And For the questions, again, I recommend to put questions in the Q&A box at the bottom of your screen. This is for attendees. And then we move to the second speaker, and the discussion will be made later on at the panel discussion level. So the next speaker is Professor Marco Mazzotti. He's a chemical engineer and has been professor of process engineering at ETH Zurich since 1997. He was coordinating lead author of the IPCC Spatial Report on CCS, president of the International Adsorption Society, and chairman of the board of the ETH Zurich Energy Science Center for 7 years. Having strongly worked for it, he is a contributor to the 2007 Nobel Peace Prize awarded to IPCC. He has published more than 350 papers, cited more than 1,800,000 times, and has been the supervisor of almost 50 doctoral students. He is going to talk about the status of carbon capture and sequestration projects worldwide. Please, Professor Mazzotti.
So good afternoon to everybody. And well, if I can call you Nicola, thank you very much for the introduction. Thanks a lot for your inspiring presentation this morning. I thought it was very well done. And I'm also impressed by the presentation of Mr. Bøwadt. I find it interesting that you said that it's easy to make this decision for the policymakers. It's difficult to implement them. In the CCS community, we have been saying that actually it was easy to find a solution, but we need a political process. And you said it at the end, right? The regulations, etc. So I think that the truth is that it's difficult both technically and politically. And that's why it's so important, I think, that we talk together, right? That the policymakers understand the scientists and the engineers, and the scientists understand the political process. So thanks a lot for your presentation and for being here. Thanks for the invitation. I'm really delighted. And I have organized my talk I would like to give you 7 take-home messages. And the first is simple. You have already said counteracting climate change requires mitigating emissions as well as creating negative emissions. So to cope with all the emissions that cannot be avoided, and the chemical industry, the cement industry, are sectors that will exist also in the future in a net zero world, and we need to cope with their emissions. And negative emissions, there are essentially 6 approaches. You see managing forests, managing soil in terms of enhanced weathering, managing the ocean, and then the 2 in the middle. I'm going to talk about them. So bioenergy with CCS and direct air capture with, again, CCS. So the second message is that point source CO2 capture is feasible across sectors, and CO2 storage will be accessible at the European level. Let me say why. This is an overview of existing carbon dioxide capture and storage activities, initiatives, projects, and let me mention maybe some of them. If you look at the North Sea, we have Sleipner. That's the oldest project. I will say something more about it. We have a number of projects in the US and in Canada. These are all commercial projects, commercial operations. The biggest one is in Australia that started a couple of years back, 4 million tons of CO2 per year. And so for those who are not familiar with CCS, I mean, I've been asked to talk about this, so let me say something, even though many of you will know. Let me focus on this specific application, which is the Boundary Dam CCS project. It's a post-combustion capture application sorry, I'm trying to get the laser pointer, here it is. So that that captures CO2 from a coal-fired power plant. These are some details. 120 megawatt net coal-fired power plant, post-combustion capture using Cancel. It's an amine scrubbing process, captures 1 million tons of CO2 per year. CO2 is then stored underground in either a saline aquifer or for enhanced oil recovery. This is operational since October 2014, and there is a similar plant also in Texas at Petranova. Now, injecting CO2 underground means going very deep. You see the depth here, where the CO2 has a density more than half that of water. So it's a very dense fluid. CO2 is stored in a saline aquifer, which is a geological layer. It's a porous layer containing formation water, salty water, because it's been in contact with minerals for millions of years. And the aquifer, this light brown layer here, is sealed by a caprock, this dark brown layer that is impermeable to CO2. CO2 is trapped there based on a number of mechanisms: stratigraphic trapping, capillary trapping, dissolution, and mineralization. So this is something we know how to do it, and but we can also capture CO2 from air. Actually, this is a plant close to my hometown, close to Zurich. The company Climeworks captures CO2 directly from air using this type of devices, modular devices. This plant captures not 1 million, but 1.5 thousand tons of CO2 per year. The technology is not absorption, it's a vacuum temperature swing adsorption, adsorption, with regeneration at about 100 degrees. This is operational since May 2017. CO2 in this case is used in the greenhouses that you see here. So it's not stored underground, but they're building a plant of a higher capacity in Iceland, where they will implement indeed capturing CO2 from air and storing it underground. So storing CO2 underground, is it safe? That's a key question. And I would like to answer yes, loudly, for 5 reasons. First of all, climate protection. Putting CO2 in deep geological formations is a lot safer and better than putting the same CO2 into the atmosphere. We know that. There is a physical basis. CO2 is trapped in microscopic rock pores by the same processes that have trapped the natural gas for millions of years. And we know them, And we have operational experience. For more than 20 years at Sleipner and elsewhere, CCS has worked. Let me show you what happens in Sleipner. Sleipner is an offshore gas field in this position between Scotland and Norway. Gas is produced from very deep underground. It's extracted, and on this offshore platform, the 9% CO2 is removed, separated from the gas, and then it's transported as a liquid natural gas to the shore. And CO2 is re-injected in an aquifer, which is not coupled with the natural gas reservoir. It's only 1,000 meters below the seafloor. It's an aquifer, so a porous structure sealed by a caprock, as I described. This structure is huge. Its footprint is this yellow kind of island. It's not an island. It's the projection of the Utsira Formation, this aquifer, and this has been operating since 1996. 1 million tons roughly per year, so it's more than 20 million tons of CO2 that have been stored there. It's been heavily monitored through seismic projections over the years, and this seismic, without going into the details, both vertical sections and horizontal sections, they show that CO2 migration follows the design specifications. CO2 migrates and exactly where we expect it to do. So it's a very successful operation, and that has been repeated in other sites, as I mentioned. I would like to mention another type of technology that is implemented in Iceland in the CarbFix project. So this is a sketch. Let me focus on this part, which is the current one. This is the future. So in Iceland, they started in 2012. They have a geothermal power plant about 30 kilometers from Reykjavik, where the steam that comes from the subsurface contains CO2 that is removed here. And then CO2 is dissolved in groundwater. You see the water here, and then it's injected underground in basaltic rocks. So it's a tighter formation, but the reactivity of CO2 dissolved in water with these rocks is actually very faster than in other formations. So the carbonation reaction that you see here leads to mineralization in less than 2 years. And mineralization, of course, is fixing CO2 as a solid, as a rock. it's really permanent, right? There is no migration after mineralization. Now, the project was upscaled after the successful test in 2012 and 13, was upscaled in 2014. It currently captures and stores 1/3 of the emissions of this power plant, which is about 12,000 tons of CO2 per year. What are the perspectives? Well, they're going to couple direct air capture. You see the direct air capture here. Actually, as I said, Climax is building a big plant there. So they will couple direct air capture and mineral carbonation undergrounds to achieve a negative emission pathway. So CO2 from the atmosphere through the direct air capture unit into the subsurface mineralized. We remove CO2 from the atmosphere. And they want to move offshore because they don't want to use only groundwater. They would like to use seawater, and they will do it to enable the injection of CO2 in submarine basalts, which are in a great quantity. And we are going to be involved in this project soon. So that tells you about the operational experience that is coupled, as I mentioned, in the case of Sleipner, with geophysical monitoring that allows us to see that CO2 behaves as expected. And finally, this has allowed to reach regulatory compliance, both for Norway and in the European Union space. So this is for CCS, but I would like to mention also utilization. It's a topic today. It's a very important topic. And I would like to underline the fact that the utilization of CO2 is very energy intensive. And for this, we need the clean energy, and we need a system level analysis to make sure that when we utilize CO2 again, we are doing something positive for the climate. And one way of looking at this system perspective is to realize that using CO2 implies capturing CO2, converting CO2 to a carbon-rich product that is used and typically generates a waste that leads to disposal of CO2 at the end. We need a lot of energy because the ground state of the energetic state of CO2 is very low with respect to hydrocarbons, industrial chemicals, carbohydrates, a little less for urea. The only compounds that are less, let's say, converting CO2 into carbonates is actually an exothermic process. And that's why actually making from CO2 construction materials carbonates is attractive, and there is a lot of activity in Europe and worldwide, and also in Switzerland on this. CO2 conversion, again, consists of steps. Typically, we need to react CO2 with hydrogen. Hydrogen has to be carbon-free, has to be clean, and we need to harvest the renewable energy in order to enable this. So let me give you the fourth message. So how can we achieve carbon dioxide removal to generate negative emissions? Well, there are two ways. One I've mentioned, direct air capture. I don't explain it again, but we take CO2 from air. Of course, this requires energy, so it has an energy cost beside an economical cost. The other possibility is to use biomass. And I want to give you a specific example, which is very important in many European countries. Waste to energy plants, so waste treatment plants. This is a very schematic representation of a waste incinerator that receives essentially two types of waste, municipal waste. And I take a table as an example, a plastic table that contains fossil carbon, right? And a wooden table that contains biogenic carbon, ultimately coming from the atmosphere when plants have uptaken CO2 and transformed it into cellulose, for example, through photosynthesis. Now, when we burn these two objects, we produce fossil CO2 and biogenic CO2. And in Switzerland, it's about 50-50. So if we equip a waste-to-energy plant with a CO2 capture plant, the same that we have seen a post-combustion capture plant, and we store the CO2, we are avoiding emissions for the fossil part, and we are generating negative emissions for the biogenic part. And these emissions in European countries are significant. It's a type of BECCS, bioenergy with CCS, that can be important to enable sustainable cities and sustainable communities, because a waste treatment plant disposes of the waste, recycles precious materials, generates heat and power, and can mitigate CO2 and generate negative emissions. And biogas upgraders have the same type of configuration. So when we talk about BECCS, many people think of competing with food production. Well, there is a lot of BECCS that can be realized in Europe using biogenic CO2 that we have in our hands, because it comes in the biogas plants, in the waste treatment plants. Chemicals. I would like to, of course, it's very important that we develop ways to reuse CO2, but I would like to advocate the fact that we need to keep an open mind and look at really what the best option for the climate is. And I would like to take an example, methanol, an important commodity. Today, we don't make it carbon neutral, right? We have a fossil source that is transformed in a petrochemical plant in methanol, this blue arrow, which is used somewhere, and then at the end, CO2 is emitted, right? That's today. If we want to make net zero CO2 methanol, we need to do something. And there are three ways of doing this. The first is by recapturing the CO2 that is emitted here, recapturing it through a direct air capture plant. We need a little bit of energy, and then store it underground. So this is a CCS solution, storage with direct air capture. Another possibility is that of capturing the CO2 from air, but instead of storing it underground as here, using the CO2 to make methanol. In a different plant, it's a plant that converts CO2 into a chemical, in this case methanol, then methanol is used, emitted, and this cycle is driven by a large amount of energy, electricity effectively, that we need for the conversion of CO2 into methanol. The third possibility is using biomass and making biomethanol. This plant is different than this one and this one, right? It's a biorefinery, essentially. We will hear about this in a few minutes. And in this case, the responsibility of uptaking CO2 back from the atmosphere is delegated to plants and vegetation and crops, right? So we have three options. And if we evaluate the energy intensity and requirements of these options, including today basically we don't need much of energy because the energy comes with the fossil fuel, right? In the CCS direct air capture solution, we need a little bit of power in purple and some heat in red. In the bio case, we need a little bit of energy, electricity, and very little amount of heat. In the case where we want to reuse the CO2, we need a lot of electricity, essentially to make hydrogen. That's the key step. The hydrogen synthesis eats all this electricity, and then we need heat for the conversion and other functions in the process. It's important that direct air capture is needed in both these two cases. Now, of course, energy requirements are one criterion. If we looked at these, we would say, okay, bio is the way to go. And certainly in certain countries will be the way to go. But there are other factors. And another important factor is land use. So if you look at, because to harvest this renewable energy, renewable electricity, we will need a certain amount of land to install solar panels, for example. In the case of methanol is a good example because we have all the data. We can do these calculations very easily. And it's about 70 square meters per ton per year of methanol produced. In the case of CCS DAC, what we need is storage, but it's not really critical, the land above the surface. The problem is with biomass, right? Because for the same amount of methanol, 1 ton per year, we need 2,500 square meters. So we have different solutions with different pros and cons. Let's keep our minds open to find the best one. Keeping in mind that as soon as we need electricity, if the electricity is not carbon-free, and this is shown in this diagram, the horizontal axis is showing the carbon intensity of electricity. And the average Europe is here. EU28 is today here, 0.4 tons of CO2 per megawatt hour. Of course, the emissions associated to the production of methanol with these different techniques changes, right? So today, we are not using electricity at all. So basically, the emissions associated to the production and the use of methanol are constant. If we do, if you use biomethanol or we implement a solution using CCS and DAC that are little, they don't need a lot of electricity, well, the emissions increase with the carbon intensity of electricity very slowly. But in the case of CCU, they increase very fast because we need a lot of electricity. And you see that for the Europe, for the energy mix of Europe today, the emissions, so the loop, this circular economy around methanol today would emit at the end twice as much CO2 than the current solution where we don't care about the CO2. We produce methanol from natural gas and we emit the CO2. So only countries that have a very low carbon intensity of electricity, like Switzerland and France, would benefit from this solution already today. So it's clear that we need to move this average to the left. We have to reduce the carbon intensity of electricity, but we need to be aware of the amount of electricity that we need to make chemicals in this way. Sixth message is about jet fuels. I just give a sentence, and you can look at this publication. We had a publication also on the previous topic. It's here, a recent publication. So jet fuels is a special type of chemicals. Synthetic fuels are considered very appealing, but we have done a careful calculation of the cost, and synthetic fuels are the least cost-effective option, unless there is a very high carbon tax that makes it make them feasible. That's where the policy comes into the picture, right? Again, final message. It's not the final message. It's my. I have another one, but basically, I'm going back to this picture now of the three options to make net zero CO2 emissions, chemicals or jet fuels. We have three options. The key problem for the bio option is the land use. The key problem for the CCU, so utilization, recycle of CO2, is energy. We need a lot of energy. It has to be carbon free. The problem for CCS DAC is CO2 storage. We need to have an availability of CO2 storage. So I'm not arguing that one is better than the other. There might be different situations where one is better than the other, but we have to keep in mind one thing. I mean, Nicola said at the beginning this morning, the challenge is, I think you said gargantuan, right? It is, because we have to make a lot of changes. Now, the solution with CCS DAC is the only one that doesn't need to rebuild the chemical industry. We can use the chemical industry as it is. We don't need to build a new chemical industry. And if we want to implement negative emissions, keep in mind that negative emissions are based on taking CO2 from the atmosphere, capturing it with a direct capture plant and or biomass, and putting the CO2 underground. So the CO2 storage part of the chains is unavoidable when we need to create negative emissions. So let's work also on this option. And I come to my last message, that is, whatever we do with the CO2, we want to use it or we want to store it underground, we need to take it from the sources, and we need to have a Europe-wide CO2 network that serves all CO2 sources and CO2 sinks. And this is not only a technical problem, but it's a political, it's a financial problem. But this is a picture, a projection of, I mean, these are the sources of CO2 in red, with the largest potential, but also the sources that are going to stay. I'm not showing power plants here. I'm showing waste incineration plants, cement plants, biomass and biofuel refineries, steel, natural gas, direct capture. So it's many of these emissions will stay. And in 2050, the projections are that we will have to capture hundreds of millions of tons of CO2. And most of it, or some of it, will have to be stored. And if we look at the perspective in terms of storage opportunities, we have Carbfix, I mentioned. Northern Lights will be online. It's an initiative of Equinor, Shell, and Total. Will be online in 2025, serving also sources in Europe. There are two projects in UK, Acorn and Teesside, for a CO2 storage cluster. There are two initiatives, or one initiative in Holland, and maybe one in Italy, for storage of CO2 that can serve the European user. But to get to these storage sites, we need an infrastructure. And a CO2 network that connects CO2 capture sites through a transportation chain to permanent storage sites or utilization. That's a key. That's the first indispensable element of a CO2 ecosystem in Europe. CO2 will be captured from sources and from air. It will be transported and it will be delivered to sinks where CO2 is utilized and to sinks where CO2 is stored. And this network will be connected with the natural gas grid and the hydrogen grid. And this takes time to be developed, and I think we need to start very soon. I thank you very much for listening, and I hope there will be the chance to discuss later. Thank you.
Thank you very much, Marco, for this great presentation full of important information and concepts. And I hope indeed also that we have a chance for discussion later on. Now we switch to the next speaker, who is going to be Angela Dibenedetto. And Angela is currently chair of the National Inter-University Consortium on Chemical Reactivity and Catalysis in Italy, and among other, also chair of the Italian group of carbon dioxide capture and utilization, and vice president of the International Conference on Carbon Dioxide Utilization. She's the recipient of several national and international awards and serves as associate editor and editorial board members in international journals such as ChemSusChem and Current Green Chemistry. Her main scientific interests are coordination chemistry, metal-organic chemistry, catalysis, sustainable synthetic methodologies, carbon dioxide utilization, use of supercritical carbon dioxide as solvent and reagent, and synthesis of heterogeneous catalysts. So Angela is going to talk about the carbon dioxide recycling perspective and challenges. Please, Angela.
Thank you very much, Nicola. Ladies and gentlemen, good afternoon. Let me thank the organizers for the kind invitation to this very interesting webinar. This is to introduce myself and my organization, the Inter-University Consortium on Chemical Reactivity and Catalysis, which was founded in 1994. It groups 18 universities and was recognized in 2002 by the Ministry of the University as a no-profit center of excellence in research. My research group deals with the valorization of spent carbon, either CO2 or residual biomass. And as you can see here, I show recent papers and books related to these topics. My presentation will deal the transition from linear carbon economy to circular carbon economy, considering the direct conversion of CO2, the photochemical conversion, the integration of catalysis and biotechnology, and very shortly I will consider also the use of biomass, either oily or cellulosic biomass. We have heard a lot today about these aspects. We know that humans have developed a linear concept based on take, make, use, and dispose fossil carbon. And we know that the existing technologies are very low in efficiency, and almost 70% of the chemical energy is released in the atmosphere as thermal energy. Moreover, we have heard today that we have the emission of carbon dioxide is around 34 gigatons per year, this in 2020. And so there is an urgent need to reduce the CO2 emission and its accumulation in the atmosphere. To this end, we can either introduce efficient technologies able to reduce the use of fossil carbon, or we can use perennial or renewable primary sources. For being used, carbon dioxide must be captured from continuous or concentrated point sources such as the power plant, industry, or directly from the atmosphere. And the fate of this CO2 captured is the carbon capture storage, and now is becoming imperative also the options of carbon capture and utilization. CCU differs from CCS essentially in one basic way. CCS captures CO2 emissions exclusively for storage, usually, as we have already seen by Dr. Mazzotti, usually reinjecting them into geological formations. So CCS is in line with linear economy, while CCU may represent a way to complement the natural carbon cycle, and it may offer the possibility to go from the linear to circular economy by using the renewable carbon, which can be then used as a source of energy for its conversion. In the view of circular economy, CO2 is considered by the chemical industry not anymore as a waste, but as a building block or source of carbon. In fact, it can be used. It is used for the production of chemicals at commercial level. Of course, there are several efforts to react CO2 with olefins, dienes, alkenes to obtain carboxylates, carbonates, and carbamates. But all these processes require active catalysts, and also they are not. It is not easy to implement these kind of processes because some of them are endoergonic. And so the CCU may represent challenges, an alternative to produce chemicals, materials, and fuels by direct conversion of carbon dioxide. Or we can also let nature to fix CO2 and use chemistry to convert the biomass. And what is very important that I wanted to stress is the integration of chemistry and the biotechnology. In fact, whatever we do, we have to face the issue of one extra oxygen atom. This also when we substitute hydrocarbons to carbohydrates or CO2 to CO. What we need are the new catalysts, which can be very active for new catalytic processes. So the CCU concept has the potential to shift the way we consider carbon dioxide. It is a source of carbon, it's not a waste. And the CCU afford the possibility to have fine chemicals, bulk chemicals, materials. It may reduce fossil fuel extraction and also the dependence on natural reserves of carbon, reduces the CO2 emission into the atmosphere, and also may contribute to development of CO2 water economy. So the table here gives some amount of the carbon dioxide which is actually used to make chemicals, and also present a forecast calculated considering the expected market growth for this kind of chemicals, and assuming also that the new technologies that can be developed will be able to convert large volumes of CO2. And of course, we have already heard by Dr. Mazzotti that when we use carbon dioxide to make chemicals, we have to consider the energetics. In fact, here you can see some Gibbs standard free energy of several C1 species, and it's quite evident that when the oxidation states of carbon atom remains around 4, which is the oxidation state of carbon in CO2, the reaction may be exergonic. Conversely, when it is reduced from +4 to +2 or lower, a significant amount of energy is required, and together with energy is required also hydrogen. So we can classify the reactions for CO2 conversion in 3 classes. The class A in the class A are considered the low energy processes, which are on stream. In the class B, the decarboxylation processes, and in the class C, the high energy processes. In order to develop the process listed in the right part of the slide, it is necessary to have cheap hydrogen available, and also only if this hydrogen is generated from water using perennial energies, then all these processes can be developed. Another important point is the source of CO2. Several industrial processes produce significant amounts of carbon dioxide with high quality, and this can be used immediately with a very low cost of recovery. So the new process can be evaluated by using different key performance indicators, such as the E factor, the ratio between the waste produced per unit of products, the carbon footprints, the energy consumption rate ratio, the carbon fraction utilization, and also very interesting, the ratio between the avoided amount of CO2 with respect to the amount of CO2 used, which is ranging between 2 and 5, with a good average around 3.5. And considering these possibilities, we can speak in terms of sustainable chemical and polymer industry, which is able to have for the bulk chemicals, such as those I have depicted here, carbonates, carbamates, formic acid, acrylic acid, olefins, and also carboxylates and monomers and polymers, and also fine chemicals such as lactones, pyrones, and pharmaceuticals. An important aspect to consider is also the carbon retention of CO2, because it can vary per product, ranging from less than 1 year if we use, for example, CO2 to make fuels, or for more than 10 years if you use CO2 to make polymers or also building materials. And this could be, this is a key point to consider. Now I will move to discuss some processes related to the conversion of carbon dioxide into chemicals, which have market around 1 million tons, such as dialkyl carbonates. Here you can see the reaction where CO2 is reacted with an alcohol, a generic alcohol. The reaction meets the principle of sustainability. Also, if it has an unfavorable thermodynamics, in fact, the equilibrium concentration of the carbonate is low, is around 1% or lower, depending from the reaction conditions and catalyst. The only co-product is water that should be removed. in order to shift the equilibrium to the right, and also to avoid the activation of the catalyst. Several aspects have been considered, and several solutions have been proposed. Among them, the use of organic traps, or also the use of pervaporation membranes, that seems to be a good way to increase the productivity of the process. And here you can see a flow system we have set it up, where a pervaporation membrane has been inserted into the cycle to increase the amount of diethyl carbonate obtained reacting bioethanol derived from a fermentation process and CO2. Interesting is also the use of urea instead of carbon dioxide, as urea can be considered an active form of CO2. As a matter of fact, urea has been used in several applications, bringing the synthesis of carbonate from alcohols to the demo plant level. The reaction mechanism has been investigated in details by several authors, and and further studies are still in progress for better understanding the potential of such methodologies that requires the recovery of ammonia for reaching an economic acceptation. As a matter of fact, the conversion rate is higher than the reaction made with CO2, because the thermodynamics is better, and also because the reaction is not equilibrium driven. Considering the forecast, has been calculated that the amount of carbon dioxide needed to convert to be converted is lower with respect to the amount of carbon dioxide available to use. So in order to change direction, we have to consider the possibility to use a different source of energy always available and at low cost, such as sun and wind, and also we have to develop such processes able to storage solar and wind energy into chemical bonds. So this means that the high energy processes for CO2 reduction are feasible, and so at the moment chemists have to take this opportunity. And so far, we spoke about dark chemistry to make chemicals, but now let's go to light chemistry to make fuels, of course, by using low entropy CO2. And alternative route to large-scale CO2 reduction can be the water electrolysis via PV, and the use of PV hydrogen for the thermochemical conversion of CO2 into energy products. As an alternative, also CO2 and water coprocessing could be considered, also if deep investigations are required because the conversion yield is very low at the moment. And this can be carried out by using electrochemical, photochemical, and photoelectrochemical systems. The co-processing of CO2 and water that can be considered as a one-step, one-pot process eliminates the need to produce, store, transport hydrogen, which is a key point, and represents the real innovation in the field, mimicking nature. And an interesting approach is also the photocatalysis coupled with the use of solar energy that may offer interesting perspective in this area. Recently, the direct insertion of CO2 into CH bond of organics have been shown to occur under photocatalysis. Very interesting is also the photoreduction of CO2, where when CO2 is converted into methane or formic acid, and as electron donors is used waste organics, which is also oxidized in useful products. Interesting is also the hybrid system used for the enzymatic reduction of CO2 to methanol in water that combines two processes, the enzymatic reduction of CO2 into methanol by using a pool of dehydrogenases enzymes, which are NADH dependent, and the presence of a photocatalytic system able to regenerate the NAD+ into NADH that can be used again by the enzymes. And interesting, so the integration of biotechnology and catalysis can be a very interesting approach for the conversion of carbon dioxide, as catalysis can be considered as a tool for accelerating bioprocesses, and bioelectrochemical systems can be considered useful to provide hydrogen for CO2 conversion into C1, C2, or CN molecules in general. An interesting approach is the use of biomass that is able to fix CO2, and we have seen that when aquatic biomass is used essentially to produce fuel, the approach is not economic, is not affordable from the economic point of view. But if we applied the concept of biorefinery and the fractionation, and considering the possibility to use all fractions, all components of the biomass, cellulose, proteins, and lipids, the economics of the systems may change a lot. And in fact, if we consider the lipid fraction, and in particular by using the saturation or unsaturation moiety of the triglyceride, we can obtain a variety of molecules such as pelargonic acid, azelaic acid, that are very interesting molecules for industrial application, but also is possible to obtain by considering the last part of the slide, the polyepoxide that can be converted into polycarbonate and also in polyurethanes that can be labeled as bio-based polyurethanes. And also is possible to obtain biodiesel and glycerol. This glycerol can be converted again using the integration of biotechnology and catalysis, because through biotechnology, glycerol can be converted into 1,3-propandiol, and through catalysis, 1,3-propandiol can be converted into 3-methylene carbonate, reacting 1,3-propandiol with urea in presence of an active catalyst. And this carbonate is very interesting for polymer chemistry. Another example is the use of cellulosic material, which can be hydrolyzed by by microbe into C6 and C5 fractions, and then the catalysis, the chemocatalysis can convert these fractions in platform molecules such as FDCA, which can be considered a new monomer for polymers. So this approach, the integration of biotechnology and catalysis, seems to be a very appealing approach. In fact, in bioelectrochemical systems, bacteria interacts with solid-state electrodes by exchanging electrons with them, either directly or via redox mediators. So in conclusion, we have seen that CO2 is a valuable source of carbon. It is already used in the chemical industry at a rate of almost 200 million tons per year. It is possible that by using the existing knowledge, the expectation is to cover a large volume of CO2. We have seen that nature makes from CO2 1,000 compounds using solar energy. And so the combination of solar energy with catalytic conversion may bring to the reduction to fuels, enlarging the utilization to several gigatons per year. Interesting is also the use of hybrid catalysis and biotech that may open a new scenario in CO2 conversion into energy products. Thank you very much for your kind attention.
Thank you very much, Angela, for giving us the wide range of opportunities we have by converting carbon dioxide, which is really, really, really big and interesting. A lot of research to make here. Now we move to topics related to agriculture, and our next speaker is Robert Mbarek, who is an agricultural economist at the European Commission's Joint Research Center, Directorate for Sustainable Resources in Seville, Spain. He received his PhD on EU trade relations from the University of Hohenheim in Germany. Since many years, he has been coordinating and involved in economic modeling analysis related to the common agricultural policy, trade, and the bioeconomy. Please, Robert.
Yeah, thank you very much for the kind invitation and introduction. So I will now try to share my screen.
Very good.
Okay, very good. So the presentation will be on biorefineries for the chemical industries. It is based on joint work with colleagues from the GRC, but also I will present some other work from BTG and EU4Tech. The presentation will start with a brief introduction on the Green Deal and related policy initiatives, which have really a very strong relation to the question of bio-based production, and in particular also biorefineries in this context, and chemicals. Briefly mention the challenge of data availability, and then give some introduction into the markets, so how they are presented within the bioeconomy, and finally, well, after a very short outlook, make a demonstration of our tool, which shows the existing chemical and material-driven biorefineries. So in the new industrial strategy for Europe, which was published in March 2020, it was written that the next era of industry will be one where the physical, digital and biological worlds are coming together. And I think we have seen a lot of very interesting and important examples of how this is working already. And just looking at the issue of biomass and the value of biomass, which also was mentioned in some of the presentations before, that we can see in this triangle or pyramid that actually fine chemicals, pharma products are on the top of this pyramid, where we have a high value added, while the volume of biomass used is rather limited compared, for example, to the use for energy. So that is something to be kept in mind. If we now look at the policy issues, and we see here how the bioeconomy contributes to the European Green Deal, we see that there are several initiatives and examples how actually the bioeconomy and with it the bio-based industry are contributing to the circular use of biomass, striving for a greener industry. It is also about eliminating pollution, and finally, that we should not forget, also ensuring a just transition for all, so creating jobs in rural areas, for example. Then if we look at the circular economy, we see that actually sustainable biorefineries can represent a key element in this transformation, making even the EU a global frontrunner. So I'm mentioning this only because we mentioned, we had before the question, so where's policy? Well, I would say it has already launched a lot of initiatives which now have been to be filled with life, and we have heard in the presentation on the research programs that actually a lot is happening. If we look at the chemical strategy, which was also launched last year, we see that that moving to safe and sustainable by design chemicals, including to sustainable bio-based chemicals, well, and investing in it, is also a precondition for reaching a clean circular economy. And finally, a very recent one on the organic production, that there is also an action which should adopt a framework on bio-based, compostable and biodegradable plastic. So there's really a lot of work in front of all of us in order to make this transition happening. And last but not least, I'd like to mention this sustainable finance and EU taxonomy, which was published yesterday. Without going into any details, I just would like to stress the importance of it, because this should create then a kind of green list, so a classification system for environmentally sustainable economic activities, a kind of common language so that also investors can use it when they want to decide where to invest, and always having in mind then a substantial positive impact on the climate and the environment. And again, here's also in the manufacturing, we see that also the manufacturing of plastics and organic chemicals are mentioned. So it is really something which is part of the whole Green Deal and this transformation of the industry towards a more sustainable one. There is a big challenge now on the data availability. We just published a paper which shows that we actually have to make our hands dirty. Yeah, that is the situation is not as good as we would like in order to make then also economic assessments of how the situation of the bio-based chemical sector looks today and could look in the future. So we have these uncertainties of the economic development, but also on the technological development. Well, in the presentations before, different options were shown. That is not the topic where I would like to talk about, but more the economic development. And then in general, in order to better understand the market and develop also policies, there is really a lack of data. So that is also something where the community together could make the difference. What we can see is that the bio-based industry in the EU, we can have here a look, has about 7.5 million workers, contributes about 400 billion of value added, and has shown quite some growth. So the latest numbers we have 5% from 16 to 17. In total, we can say that the manufacturing of the bio-based chemicals, pharmaceuticals, and rubber and plastics have a share of almost 10% of the value added in the EU bioeconomy. And well, a particular strong growth where fossil-based industry is being replaced with innovative bio-based industry is the bio-based chemical sector. And that includes also the pharmaceuticals, as we can see, which is the biggest part with about 46 billion. And that is important, not least because of the COVID crisis, but certainly also because of bioplastics, and it's a highly debated topic. So for this type of bio-based industries, biorefineries are a key industrial infrastructure. And again, just to show how also we have seen here, according to our numbers, a growth in the value added, but also in the employment. So if you look at the left-hand side, we see that bio-based chemicals, pharmaceuticals had about maybe 40% growth in value added over this period. And if we look at the employment growth, these were also the sectors which actually had some growth, whereas others, the more traditional ones, had been reduced over time. For agriculture, that shouldn't be a surprise. We have structural changes happening, but in any case, the statistics also show that this is a growing market. Talking about markets, well, we just published here a study on bio-based value chains for chemicals, plastics, and pharmaceuticals. Here, I just would like to mention the following, that actually the EU is rather well placed. So if we look now at the bio-based markets, so we can see that actually the largest share of global fossil-based chemical production takes place in Asia with about 60%, which is much higher than the European one. That would be the blue one. But then if we look at the bio-based chemicals, there Europe is much closer to the production in Asia. That is again now these blue bar compared to the pink one of Asia. And the same is then true if we look at the chemical world market, if we look at the value. Yeah, again, there the share of the bio-based market in the EU is almost as high as in Asia. So that just gives an impression of how the current situation is on the markets. Now, biorefineries could certainly be seen as one solution towards a climate neutral economy. We have seen many others, so that's why I really want to stress it is one of different possibilities. And I find this picture rather illustrative. It shows now that the sustainable biorefineries are using biomass, in particular food waste and residues or other waste, biogenic waste, and replacing therefore the fossil fuels. Again, we should not underestimate the importance of creation of crops and jobs up and downstream in the rural areas, which is from a policy point of view always a very important and strong argument. And then also the resulting products should have smaller environmental footprints. An important element is that this is also included in various Green Deal initiatives. So now I would like to present you the dashboard where we analyzed and show and can play a bit around with the biorefineries. So here you can see now a map of Europe with different dots showing where the different biorefineries, and we made a choice of chemical and material biorefineries, how they are distributed in Europe. And you can see that about a number of 300 has been identified where the feedstock is mainly coming from agriculture, as we can see, but also forestry plays an important role. Waste and marine are still smaller and certainly can then show a bigger growth potential. We also see that most of the biomass is still coming from primary biomass, as you can see in the bottom right side, and only about 20% coming from the secondary biomass. If we now go a bit deeper, so we have here chemicals, composites, and fibers, and liquid biofuels. So just to mention, biofuels were explicitly not included, but they are sometimes a co-product, so then they are included. But if not, there was really a focus on the chemical and material refineries. So if we now make a choice and go for the chemical biorefineries, we see again this distribution, in particular in the Netherlands, in Belgium, where we have a high density of different ones. And again, here the primary biomass coming from agriculture is dominating. If we, for example, then would go for forestry, we can see that actually here the secondary biomass has a much higher share. So that is an interesting result, and shows that that there are different pathways possible. Now we go back to the chemical general view. There is also the possibility to go into more details so that we can see what are the feedstocks of the different refineries in detail. And we can see that actually oil crops, starch crops, sugar crops, but then already residues from forestry are really dominating. If we look then at some further details, so here we have the possibility of, I go back, and just one second. So we go back and choose the chemicals. And here we can see now that, we have here the feedstock, as mentioned, in particular dominated by agriculture and their oil crop, starch, sugar residues then from forestry. We have some very clear preference for platforms from C5, C6 sugars, and then oils. And then finally, what we can see is that the biorefineries which produce products have also there a kind of focus on building blocks and polymers. If we now go to check a bit the distribution in Europe, we can see that in particular the biggest countries, France and Germany are clearly leading. But then the Netherlands, Belgium, Finland, Sweden, also Italy, Austria have an important capacity. Here you can see in the second bar, so these are the products differentiated by chemicals, composites and fibers, liquid biofuels and others. And then in the second one, you can see again how depending on the country, the feedstock is different. So here in France and Germany, Netherlands, Belgium, we have clearly agriculture being the most important one. Then for the Nordic countries, we see forestry the most important one. Finally, there is a possibility also to have a kind of comparison with other countries. So we have here some countries which include, which are out of the EU. So we have China, USA, Japan, Brazil, and some others. And we see quite some differences in the use. For example, on the feedstock, there is even more the agriculture in the non-EU countries. The agriculture is even more important. And what we can also see is that that in non-EU countries, the use of primary biomass is dominating. Well, that is an interactive platform where, of course, everyone is invited to have a look and then analyze how the situation is. So then I just wanted to briefly mention that we have also and I show now here that there had been a study which will be forthcoming very soon. This is a study which is led by a consortium for E4Tech. Here you have the link. And there the idea was to have also some market prospects for biorefineries. And if we look at the demand, well, there is a low and a high growth scenario. In the high case, there we have a higher support and deployment of biorefineries and an increased market share as a result of stronger drivers. Well, that is, of course, then the demand. Whereas in the low scenario, the demand is reduced and also the support would remain lower. And what we can see is that basically in the high growth scenario, there could be a tripling of the demand for surfactants, man-made bio-based fibers, resins, polymers, lubricants, building blocks, additive solvent, and others. So that is that would be an average rate growth of almost 10% per year, and certainly it would need positive macroeconomic situation in order to really create the incentives for the markets to respond to this demand. In the low growth scenario, we would remain, well, as you can see, under 8 million tons compared to the almost 6 million tons today. So this is just another possibility for the development. And well, that was more or less my presentation, where I wanted to give you a quick insight into the current situation of the bio-based industry, bio-based chemical, biorefineries, and then the policy framework, which is trying to set up really the uptake of this sector. Thank you very much.
For showing us the great opportunities that this sector has in the decarbonization process. And now we switch to the last speaker before the panel discussion. And the last speaker is Nuno Marinho, who graduated in electrical and computer engineering from the University of Porto in 2014 and received the PhD in Paris in 2018. Since November 2019, he has been working as an innovation project manager at EDP New, where he is responsible for research subjects on the economics and regulation of power systems. He is now the project coordinator of JANOS, H2020 funded research project with 34 partners from 8 countries and a budget of nearly 9 million euro. Before this experience, he also worked as a research engineer for EDF Research and Development. Please, Nuno.
Thank you, Nicola, for the introduction. I believe that you are able to see my screen already.
Yes.
Perfect. So thank you for the introduction. Thank you also for the invitation to be here with all of you today. It's been a pleasure to assist to the last presentations. I'm able to learn a lot since I graduated in electrical engineering, so I'm a little bit out of my waters in here. And today what I propose is to talk a little bit about the energy transition and do a focus on the decarbonization. And I will try to illustrate this with some of the projects that we are working. So the idea is to give the current status, the challenges, and how are we trying to tackle, and so give an overview on the energy transition. So as trying to switch it. Yeah, okay. So just to give a context of the company what I'm working at EDP, which is the Portuguese energy utility, and more specifically at EDP New, which is the branch that's dedicates to research and innovation projects. And so we are divided in different areas, and we are working mainly on competitive funding projects in those different areas of power systems mainly. So my presentation will be also a little bit focused on power systems, and the projects that I'm going to talk about after is projects that the company is working on. And so if you have any questions, then at the end, I believe we'll have time to address them. So I would like to start by the Green Deal, which has already been referred previous to my presentations. But I think that this is an important step, as when it was introduced and when we defined the goal of making Europe climate neutral by 2050, this has bring the attention of a lot of stakeholders to the need of this transition. And so the Green Deal, it brought new regulatory frameworks, funding to incentivize research and development. So it's more than just stating goals in a paper. And we have this as an opportunity for the European industry and economy. And so we see it as the pathway for the transformation of the global energy sector. And I would like to start by showing this image, which I took from the World Energy Council report on the World Energy Issues Monitor, because COVID has been the subject in the last year and something already. Unfortunately, we have been impacted by this COVID-19 situation. But this is a really interesting image where we see that actually it's just one of the waves of what we are already seeing on what is coming in the future. And one of the biggest ones that will have to face is the climate change. And so that's why we say that the decarbonization of the energy sector requires urgent action at a global scale, because we are now seeing the impact that COVID-19 has on our lives, but climate change can be something that it's even more drastic. So it is important that we take this action now. And from this same report, we can see this was published recently, and I found it interesting that they, with the questionnaires that they did, they were able to identify the subject which are the action priorities. So what keep the energy leaders busy at work, and what are the subject that keeps energy leaders awake at night. So the ones who are keeping them awake at night is the ones where there is a lot of uncertainty still. And we can see that renewable energies is something that it's already acknowledged as something with having an impact, but it's not that uncertain. But when you go a little bit above in the scale, so in the y-axis we have the uncertainty, you can see that we have hydrogen, carbon removal, carbon abatement, energy supply. So a lot of important questions are still to be answered. And so this is just the beginning. In terms of the current situation in power systems, I'm giving you here an overall picture of the situation. And in here we are presenting the share of renewables versus conventional generation in 2019. And I would like to share this image because I think that it's a common view when we are talking about where we are in this energy transition. We are mainly comparing conventional generation and renewable generation. And if we take a look at the global picture, we can see that we still have a lot of progress to do. There are some countries where I would for sure would like to highlight, for example, Portugal, where we have 50% of renewable generation already. But we then have different countries, some other countries like, for example, France, where you have 90% of renewable generation. But this renewable versus conventional is not the whole picture. We have to look a little bit more into the details. And so when we are seeing the greenhouse gas emissions intensity of the electricity generation, for example, France is one of the least intense countries because they're mainly their electricity generation is based on nuclear, which really reduces this greenhouse gas emissions. And looking at this picture, I think that it's even more illustrating of the effort that we still have ahead of us, and that we still have a lot of countries like Estonia, Poland, and Cyprus, and Greece, where their electricity generation is still emitting a lot of greenhouse gas emissions. And so this is the most important part to tackle in the near future. And for example, one of the countries that I would also like to highlight is Germany. We've been hearing about a lot about this energy transition in Germany, and the fact is that they are still one of the most intense countries. Overall, not just to paint a really bad picture of the situation, overall we can observe a sort of a good trend in reducing this intensity in electricity generation. For sure, we are still far away from our final goal, but the trend over the last years, we can see that sometimes we tend to stagnate, but now we are moving forward and being able to reduce the gas emission intensity in the electricity generation. And so the two dotted lines that we see are the forecasts for that the European Environment Agency provided, and that they foresee that by 2030 we would be around the 100 grams of CO2 equivalent for kilowatt hour. And so the current trends in power systems, this is something that you are hearing for the last years, several years, I would say, is that one of the trends is the investments in more wind and solar power. We see that wind and solar power tend to be complementary. So we have strong wind blowing more when, for example, in the winter when the solar energy is weaker. So it tends to be a sort of complementary between these two sources. And this is something that we can base ourselves for the decarbonization of power systems. Nevertheless, not all countries have the same potential for these renewable energy sources generation. And so the fact that we have the complementarity between wind and solar does not mean that the country will be able to have those two sources in a sufficient level for their demand. And so one of the things that we've been also seeing, especially in Europe, is the strong investment in the interconnection capacities that it's needed to optimize the full potential of the different countries. So in this way, we could profit from the good PV generation conditions in the south of Europe and the good wind conditions more in the north of Europe, and transport all these flows throughout the entire continent. At the same time, we're also seeing a new trend, which is, we are seeing for the last couple of years, which is local is good. And so we have several research projects that are focusing on microgrids and smart cities and allowing for the load management, doing citizen engagement programs, putting the customer at the center of this transition. And so this allows for a local consumption of renewable energy sources. And this is also one of the important trends that people that can install a PV panel on the rooftop are able to consume this energy. And so it's also one of the important steps for the decarbonization. And the last bullet point is something that was already discussed today, is that we need to bring people, the consumer, the citizen, at the center of this transition. And for years, we were dealing with all of those problems purely from a scientific point of view, only focusing on the equations. But it's important that everybody understands what are the issues, that everybody understands what are the solutions, and also more important, they are able to contribute to these solutions. And so it is important that we bring the consumer at the center of this transition. And this is something that we are seeing more and more every day. But these trends, they have problems, and those problems are a threat for the decarbonization of power systems. And so the first problem that I would like to highlight, which is really simple, is our costs. So we are changing from a system that was historically designed to be centralized, that now has decentralized renewable energy sources. And this causes some technical challenges. The technical challenges are not impossible to solve, but it costs money. And the problem of costing more money is that at the end of the day, we need to ensure, once again, that the consumer is able to pay their energy bill, it's able to heat their house during the winter. So the cost of the system is really important, because at the end, this will be reflected by the end consumer. So this is the first point. Then if we look at, for example, when we are trying to maximize the potential between the south and north countries of Europe, we have a lot of costs in infrastructure to reinforce those interconnections. We need to put a lot of money for this new infrastructure. Nowadays, we have also a lot of problems with public acceptance of building new infrastructure. And one of the most known cases is Germany, with a bottleneck between the north and the south of the country, giving their high renewable energy generation on the north and their consumption points more on the south. And so this is also something that is delaying the energy transition. And one important point that I would like to also to raise, which is a problem, is that when we are thinking about all these solutions, we have to take a look into the global picture. And self-consumption is something that's really positive. We are empowering consumers. We are saying that they can produce their own electricity, but it can also be a problem for the ones who are not able to install those PV systems. We have a large infrastructure, so the electricity network, which costs a lot of money to maintain, and those costs are divided by all the consumers. If we start putting people out of the network, people have money to install those PV systems, the only ones that will be left to pay for the whole infrastructure costs will be the ones that are not able to afford a PV system. And so energy access, energy equity is something that is also we should keep in mind, and is one of the problems that we are facing nowadays in this road to decarbonization. Now I will illustrate this power system decarbonization projects with one of the projects that we are working on, which is the EU CEST Flex. And I believe that this is gives a nice example of how are we tackling these problems, these difficulties. More specifically, in here we are seeing how are we tackling the technical issues of integrating high levels of renewable energy sources. And so in this project, we are developing a virtual power plant. So with this virtual power plant, we are combining two generation sources into a single one. We are using wind farms, which have a variability in their generation, with a pump storage power plant. And so with this, we are able to compensate the possible deviations from the wind park, and being able to provide more services to the system, being able to reduce the overall cost of this exploitation. And so at the end of the day, reducing the cost for the end consumer and solving the security issues that might arise with the high penetration levels of renewable energy sources. Now, we are focusing, for the last couple of slides, I was focusing on Europe, on power systems in Europe, and for continental Europe also, but we have to take once again, looking at the whole picture and see that there are different realities. In here, I present some 4 figures, which are from a report from McKinsey on how to decarbonize global power system. And we see the total cost of power by technology type. So the different colors represent the different technologies. And then on the y-axis, we have the cost. And on the X, we have the years and the percentage of the decarbonization. And we see that to reach the decarbonization at 100%, it will highly depend on the type of market that we are facing. For example, if we look at baseload clean markets, where we are talking about like countries, for example, France, which has a base load of nuclear, which is already clean, to reach the decarbonization, we have an increase in the cost. Thermal heavy mature markets. So in here we are, for example, seeing the case of Germany. We also see an increase in the cost to reach this decarbonization. If we look at the other side, we have large diversified markets. So the part where we see a slight reduction on the cost. And these are, for example, countries that still have a lot of potential for development. So a lot of land to install all these different sources, a lot of possibilities to diversify their generation sources. We are seeing a slight reduction on the cost, but not really that significant. And last, I would like to present the example of islanded markets. So islands nowadays are a really particular part of this energy transition that sometimes tends to be forgotten. And we see that with the roadmap to the 100% decarbonization, we can see an important reduction in the costs of these islanded markets. And we'll get back to this island situation in a couple of minutes. So just to emphasize this, that we are looking into different realities, and this is something that we should also keep in mind. And I always like to use this sentence when we are talking about all the problems that we have in Europe for the decarbonization, is that in Europe we are searching for greener energy, but there are other countries where they are just looking for energy, not green, just energy. And this is important to keep in mind, because as I will say after, this energy transition is not only Europe, it should be worldwide. And so when we are moving forward, when we are seeing the challenges that we have to solve, we have to think at a global scale. And with this, not only focusing on Europe, I would now like to give an example of islands, so geographical islands, and also in the same view that it is important that we bring everybody on board. So just to give a context, we have almost 3.5% of European citizens that live in geographical islands, and the energy production costs are up to 10 times higher than on mainland. And this, for sure, is a problem. This is part of EuChemS, so I will illustrate again with another project that we are working on. And so the road to decarbonization, it's harder on these islands because the territories are small, they are not interconnected, so they are mainly isolated. So this poses a lot more technical challenges, which need to be solved in the near future. And so the challenges are mainly the high dependency on fossil fuels, which justifies the fact that when we are reaching the 100% decarbonization, the cost reduces because we are getting rid of these fossil fuels that costs a lot more. But we have really a lot of technical challenges to solve. And I think I'm reaching my time limit. I will finish briefly. So this project will have 2 lighthouse islands where we have the main demonstrations. So one in Terceiro, which is a Portuguese island in Açores, and the other one, Ameland, in the Netherlands. And then we have 3 fellow islands where we'll do replication plans. But I would just like to give an overview of what is going to be done. So I present you a list, and I will not go over it, of the different technologies that are going to be integrated. And I would just like to highlight that for each of these technologies, we are seeing improvements. It can do the same thing as the previous version, but in a more efficient way. We can integrate it in a better way. And so the main challenge of this project is to put every single one of these assets together and build a virtual power plant. So in the other project, we were looking at a national scale, and we were putting together a wind power plant and a pump storage hydro power plant. And here we are putting together as a unique power plant everything that goes within this list. So electric vehicles, electrochemical batteries, flywheels, PV panels, putting everything together. And for sure, this represents a really large challenge. So to conclude, I would just like to share some final thoughts. Once again, I would like to reiterate on the sentence that decarbonization of the energy sector requires urgent action and then on a global scale, and that we must accelerate the pace of this transition. Then we have different vectors of the decarbonization, and we must explore these different vectors, and every effort is important. And I would like to raise this because sometimes we tend to enter in a sort of war between the different vectors of decarbonization, and the same thing regarding technologies and the different leads on how to reach the better solution. And we must keep moving forward and explore every possible trend, because every effort is important. And the R&D is and will remain important throughout this journey, as breakthroughs are always needed, because as you see, we are slowing down this transition because we are still having a lot of problems in integrating all these solutions. If we come up with a breakthrough in a certain technology, we can be able to go a lot faster. And for sure, this might represent higher costs. And we may ask ourselves the question, what are the costs that we are ready to support for this transition? But the other question is, are we ready to support the consequences of not engaging in this transition? Are we ready to face this wave of climate change? And the last thought, which is something that has already been shared previously, is that we are in this together, and we are in this together in every way: academia, industry, Europe, the rest of the world, electrical engineering, chemical engineering. Everybody is on the same board, on the same boat, and so we need all to make an effort to move forward. And so with this, I finish my presentation, and I guess that we'll have briefly the time to discuss. Thank you.
Thank you very much, Nuno, for this inspiring lecture, because we have really a big transition to make, and we are not running fast enough, as we already pointed out several times, but we have many possibilities and many opportunities to improve this, especially with research and development. Now I would switch to the panel discussion, and for this, in the meantime, we have the last question for today as a poll. So please answer this question. Thank you very much. And now I leave the stage to our president, Floris Rutjes, and who is chairing our panel discussion. Please, Floris.
Yeah, thank you very much, Nicola. Of course, there's not so much time left for the panel discussion, but all the talks were very interesting. We learned more about the Green Deal, about carbon capture strategies in combination with utilization. We have some examples of how CO2 can be utilized for chemical products. We have also seen how a bio-based economy could work, and in fact, there we saw that we are, I think, quite well underway to realize this, and that is also really an opportunity. But it was also really focusing on chemical products and not so much on energy. But then I think in the final lecture it also became clear, and I think that was also clear from the lecture of Marco Mazzotti, that that when it comes to energy, the problem is far from solved yet, and that also sort of boils down to the question that Nicola raised in his very first introduction of the fuel that is required for this large ship, for this tanker, for this container ship, and that it's not so easy to generate this energy in a sustainable manner. And so maybe that is a first question that I would like to ask the panelists, the speakers of this afternoon. How do you look at this 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 energy problem that we in fact are facing. So Marco, maybe you could go ahead and so you left it sort of in the middle where this energy would come from. You showed that a lot of land would be required if you would let the energy come from biomass. There are some alternatives. What do you think?
Well, that's the easy question to start, right? Well, I think we have to go renewables. That's clear. And I've tried to indicate that we have maybe more biomass available without growing biomass for the purpose of having more energy. We have a lot of biomass available that we could use. For example, in my country of origin, in Italy, we landfill. I mean, we waste ends up in landfill, right, rather than being incinerated. I think that the second route is the correct one, because you get rid of the waste and you can recover energy from it, and you can also recover CO2. But that doesn't solve the problem. So it's clear that it's a difficult question, and mine is an easy answer. And I know that the national policies are very important and very different. But it's clear that wherever the energy comes from, it has to be clean. So if there are countries that still want to use fossil fuels, they need to capture the CO2 and put it away. Otherwise, we are not going to solve the climate crisis.
I have a question, Marco, about this. You showed the facility in Norway where they have been storing carbon dioxide for several years. And the question is, what is the cost? Because when I think about Norway, we know that it is possibly the richest country on earth nowadays, because they have this huge sovereign fund, which is real money. It's not stamped money, okay? So they have cash and they can invest. So can this, based on the cost of the technology, is it affordable in the future for every country, or still this is not completely clear how much it will cost? I read yesterday that Exxon asked a loan to the US government yesterday, I think that it was in the news on Bloomberg, of $100 billion to make a CCS facility in Texas with underground disposal under the sea. But which is the country that can warrant 100 billion in money for a private company to make something like that?
Well, I would like to answer, thanks for the question. I would like to answer in two parts. The first part is that whatever we spend today to manage and handle the CO2 and put it away is less than what we will have to spend if climate goes out of control. You know, that's clear. All economists say that, and so we should put your question into this perspective on the one hand. But of course, the question is relevant. Let me tell you, Northern Lights, which is the first project that will offer storage site to emitters from different countries, they're talking about 30 to 50 euros per ton of CO2 for the storage. And they say openly that it's a company that will offer this service. Of course, this is for the storage part. If you the cost, or the real cost, is less, that will be the price that you and I have to pay to put our CO2 there. On top of this, you have to consider the cost for capture, which from let's say post-combustion capture from a cement plant or a chemical industry can be around 50 euro per ton, also the capture part. And then you have the transportation, and the transportation, well, depends on the distance, right? But if you take 50 plus, let's say 30, it's 80, plus you might have an additional 50, 60 for the transportation. So we're talking about the cost below the 200 euro per ton, which is, well, which is actually not that much. If you calculate how much it would impact on the operation of companies or organizations, like, for example, my school. I mean, ETH emits CO2. We know how much it is, and if you pay 200 euros per ton of CO2, it's not a lot of money. It's a small percentage, very small percentage of the budget. And of course, you're looking from the other perspective, no, of building the whole thing, that's of course a lot of money. But if you build a chemical, a refinery, a petrochemical plant, you're also going to spend a lot of money, right? But important is the unitary cost. And I think that the unitary cost is absolutely affordable. What concerns me is the infrastructure. I said it. We need to build an infrastructure in Europe. And, you know, who's going to finance it? Who's going to own it? Who's going to, what the type of governance? Where do we start from, right? That's a big question for the European Commission, I think.
Just about this, my comment on this is, it took decades, if not 1 century, to build up the infrastructure of oil and gas. But oil and gas are valuable products that are useful to make a lot of things. They have powered our civilization for almost 1 century. But building an infrastructure for something that most likely is just a waste, it's even more complicated, because who wants to move something that is basically to be forgotten underground? So that's another very critical point, I think.
You're absolutely right. I recommend everybody in this workshop to read the book written by Christiana Figueres. Christiana Figueres was the head of the United Nations Environmental Program at the time of the Paris Agreement. She has written a book 2 years ago called The Future We Choose. It's a great book, it's inspirational, and she shows very clearly that the world we are going to build by managing the CO2 and, let's say, overcoming the climate crisis is a better world. So you're right, it looks like we need to build an infrastructure for nothing, just to manage the CO2, to gain nothing. We are going to gain a lot if we manage to overcome the climate crisis. We will have a better world, a better planet. That's what we have to put emphasis on.
Yeah, very difficult to pass this message, but this is one of the toughest part of the story. Yeah, definitely.
Yeah, I think there was, I think in the Netherlands, if you, because we are still relying a lot on natural gas, if you would switch like every household from gas to like a carbon-free system, then that would cost, I think, somewhere between 30,000 and 40,000 euros per household. So that's I think what I also sort of learned from the last lecture from Nuno, that it simply requires quite an investment. Yeah.
Just as a small compliment, more the investment is also the problem that we are facing nowadays, not in my backyard. And that's the problem of public acceptance of all these infrastructures that we tend to build. Because in theory, everybody's happy to build a wind farm, but nobody wants it in their backyard. And the same thing for this high infrastructure.
Yeah, that's of course, and the more densely populated an area, the more difficult this becomes. That is also very clear. We have I think that in the Netherlands, there are not so many people against wind energy or windmills, but then if they have to be put somewhere, then it becomes problematic. And so that part of the acceptance is very difficult. Perhaps a question for Angela. So you showed all kinds of approaches to use the CO2 for use in materials or in other types of products. But if you look at the huge amounts of CO2 that are produced, so to what extent does that cover the CO2 that is produced? If you look at the volume of materials compared to the volume of the CO2 that is produced.
Yes, there are some studies that stated that the potential of carbon capture and utilization technologies that are now available utilize up to 8 gigatons of CO2 per year by 2050. This means approximately 50% of current global CO2 emissions. So it could be quite interesting amount of CO2 to be used and convert into chemicals or energy products. But the aspects that I think is important to stress is the the energy input, the requirement of hydrogen if you want to do energy products. And the co-processing of CO2 and water seems to be a very challenging process because also if at this stage the conversion is very low and there is a poor efficiency, but I think that only in this way, when you avoid the generation of hydrogen, as you can do when do the splitting of water to perform hydrogen, this can be very useful to have the cheap and available hydrogen to make energy products.
Yeah, yeah. I see that also the two people raised their hands. I would first like to give Søren the word.
Thank you very much, Floris. Yeah, I would like to come to the help of Marco a little bit, because as a matter of fact, we need to look at the scale. It may be that we have a problem with storage in big communities, and we need to store it over a long time and have big facilities and stuff like that. But there will be areas where it will simply be impossible to avoid having also a direct capture and storage facility over at least the first period of time. So for two reasons. I mean, first of all, as Angela also said, and I think everyone said this, it takes a lot of energy to generate the hydrogen to utilize the CO2 directly, but also well, now I lost that part, but also there are things about geological properties in the areas we're dealing with. I mean, some areas it will be easy to store, also potentially cheap. In other areas, it's going to be very difficult. And these things do not necessarily coincide with the energy need in that particular area. So I think that one of the things we need to look at is actually a cost difference between what it costs to make CCS and to make direct CCU. And for me, the reason for that is also that we're talking so much about renewable energy, and everyone would like to have a very, very high degree of renewable energy. But it may not be so easy, because if you have a high degree of renewable energy, which is fluctuating, then you also need a high degree of storage capacity. And these things also need to be balanced. So it's going to be a mixture of things that we're going to face in the future. And it depends on the region, on the infrastructure and things like that, exactly what kind of solution will be better in different regions. That's at least it's my opinion.
Yeah, yeah. I think maybe Marco wants to answer, and then I would like Robert to give the word.
No, I want to make another comment. Let Robert talk. I can.
Okay, then Robert, go ahead.
Yeah, thank you very much. I just wanted to mention the importance of taking into account also the commitments made for the Sustainable Development Goals. Yeah, so that the transition has to follow also this very broad and ambitious holistic picture of tackling at the same time not only the energy or the climate change challenges, but also all other inequalities and other biodiversity and whatever challenges we are facing today. So that means we need really a holistic assessment, and just thinking about Europe, where we have 80% of rural areas. Yeah? So if we don't want to get them depopulated, we have to look for alternatives. Yeah? So if we think about transforming, for example, the energy system, I'm not advocating that we should use biomass, but it is just that we just have to give also opportunities for existing structures, for rural areas, for example, in order to make this, in order not to leave anyone behind. So that is just my remark. And then to keep also one important aspect of not to externalize a problem. Yeah, so we have always spillovers, transboundary impacts, etc. So there are leakage effects, and that also has to be taken into account whenever we think about solutions. So in a nutshell, it's important to take into account all driving forces, all drivers, but also all impacts we can imagine from such a transformation.
Yeah. Then first Nicola and then Marco, because Nicola was already there.
Yes, this is about what Søren and even Marco and even Nuno talked about, which is social acceptability. You, Marco, mentioned that one possibility is to make one of these carbon sequestration facilities in Ravenna, which is 80 kilometers from where I am right now.
ENI says that.
Yeah, ENI. Yeah, sure. People are asking me about this, and honestly, I'm skeptical because, as you know, you need to make a very deep seismic investigation before assessing that place is okay. And it is well known that this region has seismic, instability. So there is already a lot of opposition against this. So I think that proposing this kind of facilities in places like that is just a waste of time, because if you don't have social acceptability, you cannot do anything. But in order to convince people, and you will hardly be able to do it, it would take anyway a long time, but we don't have such a long time. So in some cases, we are just wasting our time, and this is something that has not been undertaken, in my personal opinion.
Yeah, Marco.
So I agree with you, Nicola, 100%. I'm in Switzerland, right? And we are trying to find a place for the CO2 in Switzerland. And I'm working with Northern Lights to create this connection. Some colleagues tell me, why don't we go to Ravenna? ENI says that we have a storage site in Ravenna. And I'm telling them exactly what you said, right? Exactly what you said. But I mean, in my presentation, I had to be kind of neutral, right? And ENI says that they are developing a site there. I mention it, but I agree with your skepticism. If I can, Floris, I want to make a comment about hydrogen, because I believe that hydrogen will play a huge role in different ways, right? As a chemical, as a co-reactant with CO2 to make chemicals, for energy storage, as Søren mentioned, right? That's a good possibility of storing renewable electricity. I would like to encourage everybody to, when we talk about hydrogen, to think hydrogen has to be clean. It doesn't matter where it comes from. It can come from electrolysis, great, if you have renewable electricity that we can use for that, but it can also come from natural gas with CO2 capture and storage, as they want to do in Norway, for example, where they have a lot of natural gas. They have the possibility of storing CO2, so they can actually convert natural gas into hydrogen and transport hydrogen, or as they want to do in Saudi Arabia, where they want to transport actually ammonia and reconvert it into hydrogen. So I think it's important at the European level that we insist on the concept of carbon neutral hydrogen. That's not green. I don't care if it's green or blue. It has to be carbon neutral, right? And depending on the situation, we can choose. Because the challenge also in the case of hydrogen is to create the users, right, on the one hand, and the infrastructure to make it and transport it. Yeah, that's my comment about hydrogen.
You're clearly an advocate of the hydrogen economy, but in terms of efficiency, so there's not so much difference then between the electrolysis of water and the steam reforming of methane?
Well, of course, steam reforming of methane, you process something that has energy in it, right? So, but then of course you need to capture the CO2 and store it. So we have seen, we have a paper recently published where we showed that, for example, if you use biomass, both the biogas or woody biomass to make hydrogen, you actually generate negative emissions if you capture the CO2. So there are different options, but again, making hydrogen using excess renewable electricity is a great idea if you can do it, right? In Germany, they want to make it and store it in the natural gas grid up to a certain concentration, which is also a very good proposition, I think.
Just to put a number, to make 1 kilogram of hydrogen requires 55 kilowatt hours of electricity and 9 liters of water. So that's something which is not easy to manage. I mean, the quantities are big. That's why I made this morning in the very first slide showing how much you need to move a big cargo. So it's a lot. It's a lot.
There's no doubt that we need really big amounts of renewable energies for being able to do that. And the other thing is, and what we've not really addressed yet, is that we are going to still need to import energy in one kind of form into Europe. There's no way around that, because at the moment we are, I think the current figure is just below 80%. It's dropping, but it's still not that far off.
Yeah, whatever we decide to do, what we have to do for sure, everybody agrees on that. We have to increase dramatically the production of renewable electricity. That's the key for everything, whatever we do.
Yeah. Now, maybe that is a good moment then, also looking at the time, to give you back the word, Nicola, and to sort of wrap up this day.
Yes, well, we have discussed a lot of topics. I took some notes here, and it is difficult to make a complete picture. But we discussed on carbon, and the discussion was very wide this morning. Which color to use in our periodic table. We have had several proposals. I think that after this discussion, I tend to favor the idea of using a specific color for carbon, but of course I am open to discuss it with colleagues because it's complicated. There was one who commented, well, the periodic table of the elements is just about elements, it's about atoms, it's not about molecules. So if you start to put colors, you never stop, because you should put colors also for uranium or, you know, for phosphorus, because you can make very nasty pollutants and so on. So I mean, let's focus on that, and it's really a stimulating discussion. It is clear that carbon is a unique element, and in this very historical period. So that's something that deserves a particular attention and probably a particular call on our table. We will see anyway. We'll keep everyone informed, all the registered participants and all the people interested in the discussion. We will continue on that as EuChemS to do so. We have also an important, I liked what Søren said about the vision of the European Union about the new materials. So we have to completely change our idea of making materials. I didn't imagine even only 5 years ago as a chemist that we should start thinking about a different way of making materials. We are starting to think about artificial intelligence, to start from scratch to invent molecules and let the machines make a lot of work for us, which is really an exciting perspective. And also I liked what he said about social acceptance. That's another point that I pointed out for CCS, but it is generally true. I mean, nowadays communication is very fast, as we know, people know everything. And so we have to be open, and we have to be aware that nothing that is socially unacceptable can be done. That's quite important. What scares me, Søren, is that Europe is important. It's a big economy. It's the largest economic area in the world in a way, but we are a few. We are just 6% of the human population. So being the leaders, as you said, is very important, but it is also very difficult, because the other guys can always tell us you are just a small minority on this planet. But we have to keep on being strong and continue on this leadership on the transition and on the decarbonization. We have from the Marco's presentation, we now know that storage is a possibility. It's very difficult. It cannot be done everywhere. It's expensive. It is something that can make a better world. So there is a lot of things to do, and especially now, also the numbers are scary, because as you said, or even someone else this morning, in principle, we would need to put 2 gigaton of carbon dioxide somewhere per year for 50 years to make a difference, to stay within the Paris Agreement. And 2 gigaton is a huge amount of carbon dioxide. And the biggest plant the big plant that you showed us in Norway, we are talking about millions scale. So we are orders of magnitudes below. So that's again comes the gargantuan adjective that I gave this morning. And I was very happy to hear from Angela that we have so many possibilities. I am a photochemist, so I'm not very familiar with organic chemistry, but I understand that there are several pathways to that, and catalysis is key in doing this. And also I was glad to look at the project that have been submitted on catalysis, and catalysis is one of the key points for the European Commission to fund in this rush for new materials. I also liked the concept of taxonomy that was highlighted by Robert, because Europe has to decide which are the plans and the projects which are really environmentally sustainable and must be funded. And I think that the discussion here will get very hot in the future about any kind of thing, CCS, biorefineries, and even in general the gas industry. And finally, for Nuno, I was happy to listen about the local is good, but there are problems. And I just wanted to say that I am one of these prosumers, because I'm building a house which is energy independent, but still I will be connected to the grid. So I will pay my part for the general infrastructure. And I think this is very important, what you said. I mean, we cannot be isolated. We have to do it together, otherwise we go nowhere. So I thank you really very much for the very big amount of information, and also I thank the speakers of this morning, because all the discussion was very important, and we already had several thoughts about that and discussion this morning. And I thank really you guys, all of you, very much. And let me thank once again the colleagues of the task group on the periodic table, Christophe Copperer, Rinaldo Poli, David Cole-Hamilton, and Floris Rutjes for that, and also the Secretariat, who made a terrific job in letting us discuss together and producing so little carbon dioxide compared to coming to Brussels and discuss it, which is very good, of course. So thank you very much to Ninetta and Laura. And I thank very much everyone, and I say you hello and goodbye, and probably our president needs the very final words. Thank you very much, guys.
Which will not take that long. I would just reiterate the thanks to the speakers. So we very much appreciate that you gave presentations this afternoon, a very insightful overview of so what is happening, and so what are the consequences, and in what directions are things moving. So thank you very much for that. I indeed also would like to thank the members of the task group on the periodic table, and in particular Nicola, for chairing this entire day. And I also would like to thank the EuChemS office, Anna and Ninetta and Laura, for organizing everything perfectly. It's well, we sort of get used, I think, to organizing online events, but also this one went as smooth as the other ones. So thank you very much for organizing this entire day. And of course, also the audience for being with us. I hope it was useful. And also, I think, feel free to, if there are questions remaining to some of the speakers, I'm sure you can approach them also by email to ask some of the remaining questions, and I'm sure they are willing to answer that. Well, thank you very much.
Just one final comment, Floris. Sorry, I forgot to say that the whole day will be available on our YouTube channel to all the people. And sorry for interrupting you, but that was important.
Yeah, and then in addition to that, we had a poll on what element do you think should be in the next should be the next topic or the topic of a next workshop, and there lithium came out. Well, that is something that we keep in mind as task group. Thank you very much for attending, and well, have a nice day.
Bye bye. Take care.
Bye bye.